Hello everyone, welcome to my YouTube channel. Today I'm going to solve paper 22 9701 October November 2023. This is a theory paper, AS level. Let's start from the question number one. But before starting question number one, uh, this paper will be explained uh, in a good way. Hope that everyone finds that useful and helpful before the examination. If you have any question, please leave them in the comments below, and I will answer all the questions. More videos explaining and solving chemistry past papers 9701. They are going to be uploaded, and make sure that you subscribe to the channel to update it. Now, let's start with the question number one. Uh, the elements silicon, phosphorus, and sulfur are in period 3 of the periodic table. Describe the variation in the atomic radius from silicon to sulfur. The trend of atomic radius across period is demanded in this question. And according to the periodic table, and if we move from left to right in a period 3, we know that the proton number or the increases and the nuclear charge increases. So there are attractive forces between the nucleus and the outermost electron will also increase, and the atomic radius decreases from left to right. So we can say that atomic radius decreases from silicon to sulfur. The second part is that the melting point of silicon is 1410 and the melting point of sulfur is 113. So whenever the melting point of a substance is to be required to explain, that is linked with the structure and properties, structure of the materials. So if we look at the structure of the silicon, we know that this is a giant covalent structure, but sulfur is a simple covalent structure. The structure of the silicon is like diamond, and it is a giant covalent structure, and sulfur is a simple covalent structure. So first of all, differentiate the type of structure. So we can say that silicon is a giant covalent structure, and sulfur is a simple covalent structure. So in silicon has a strong covalent bond and weak van der Waals forces. Weak van der Waals forces are between sulfur molecules. So a lot of heat energy is required to break strong covalent bond on covalent bond than weak van der Waals forces. So we have to explain in the terms of covalent bond and intermolecular forces. Silicon is a giant covalent structure, and giant covalent structure has a strong covalent bond. So if we want to melt that substance, we have to break the covalent bond. Now the next part B is we have three elements like silicon, phosphorus, and sulfur. So total number of electrons in S subshell. The proton number of silicon is 14 and phosphorus is 15 and sulfur is 16. So just look at the electronic configuration. The 1s2, 2s2, 2p6, and then 3s2 and 3p2. So, in this question, total number of electrons in S subshells, all the shells. Now, in this silicon, it has three S subshells. So that's why 2 plus 2 plus 2, there are 6 electrons. Phosphorus is 15. So if we increase one more electron, again 6 electron in the S subshell. Sulfur is 16. If we increase one more electron here, 4, 3s2, 3p4 is the electronic configuration of sulfur. Definitely, the number of electrons in S subshell will remain the same. So 6 electrons in S subshells. There are 3 S subshells, 1s, 2s, 3s. So every S subshell contains 2 electrons. So in total, we have 6 electrons. Now the total number of electrons in P subshells. As we can see that in the case of silicon, now this is 2p. Okay, let me again. Now this is silicon. So silicon has 2 electrons. Now 6 electrons are in 2p, and then 2 electrons in 3p, 6 plus 2, 8 electrons. Then if we do it 3p3 for phosphorus, it must have one more electron, and then sulfur has 2 more electrons than the silicon, so it has 10 electrons in p subshell. Now complete the table. Okay, we did it. Construct the equation to represent the first ionization energy of silicon. The ionization energy is the energy which is required to remove 1 mole of electron from the 1 mole of gaseous atom. So this atom must be the gaseous one, silicon gaseous atom, 1 mole of electron, and to form 1 mole of gaseous 1 positive cation. So this must be 1 positive cation. This is the way that two people can represent the first ionization energy of silicon. So silicon must be the gaseous, then 1 electron, then silicon 1 positive gas. Then three possible values for the first ionization energy of phosphorus are given. Circle the correct one and explain your choice, including a comparison of your choice chosen values to those of silicon and sulfur. Now, if we look at the graph of the ionization energy, you know that the third period graph is like this. This is sodium, this is magnesium, then aluminium, then silicon, then phosphorus, sulfur, chlorine, argon. So there are two exceptional cases. General trend of the ionization energy is that it increases from left to right along a period, but there are two exceptional cases, magnesium and aluminium, and then phosphorus and sulfur. Uh, if we compare the ionization energy of phosphorus with, according to this table, phosphorus with silicon and sulfur. So look at this phosphorus. This is the phosphorus. So we have to predict the first ionization energy of phosphorus. So first ionization energy of phosphorus is more than the sulfur and silicon. As you can see in the graph that it is more than the sulfur and silicon. So just have a look that more than the sulfur and silicon. So silicon is 786 and sulfur is 1000. So more than 1000. So these two values are less than 1000. So this is more than 1000. So this is the ionization energy of phosphorus. That's ionization energy of phosphorus is more than the sulfur. Ionization energy of sulfur decreases. Explain your choice, including a comparison of your chosen values to those of silicon and sulfur. So if we compare the value of phosphorus with both silicon and sulfur, we know that the phosphorus, it has now here is a silicon, this is 14, this is 15, and this is 60. These are the proton number, and you can also see the nuclear charge as well. So phosphorus has more nuclear charge as compared to the silicon. So this is the first point. We can represent the first point that phosphorus has more nuclear charge than silicon. This is the first point. So if it has more nuclear charge than the silicon, definitely it must show the greater attraction of nucleus with the outermost electrons. Outermost electrons. So that's why the ionization energy of phosphorus is higher than silicon because more energy is needed to remove the outermost electron. Then if we compare the phosphorus and sulfur, the electrons, outer electrons of P are in 3p. This is 3p3 is the outermost electronic configuration. Then of sulfur is 3p4. 3p is half filled, or we can say that this is a singly filled orbital, and this is more stable, more energy needed. A paired electron in 3p of sulfur, so less energy needed due to electron spin repulsion. In the phosphorus, it is half filled, or the electrons are singly filled, so they are more stable. And in sulfur, there is a paired electron, and due to the electron spin repulsion, less energy will be needed to remove that electron. You can make a short statement as well. Now, identify the chemical responsible for the misty fumes. So, SiCl4 and PCl5 each react with the water, forming misty fumes. So, SiCl4 and PCl5, they both react with the water to form hydrogen chloride. So, HCl is responsible for these misty fumes, hydrogen chloride. Then to predict the shape of SCl2, S has 6 electrons, so these are the 6 electrons. Then two electrons are busy with chlorine. So we can say that SCl2, it contains 2 lone pair and 2 bond pair. This is the structure like water. Water has also 2 lone pair and 2 bond pairs. So the shape of the water is non-linear, and as the structure of SCl2 is similar to the water, so that's why it contains 2 lone pair, 2 bond pairs, so the shape is nonlinear. Let's move to the second question. Second question is that the nitrogen monoxide and nitrogen dioxide react at 25 degrees Celsius to give N2O3 dinitrogen trioxide, and there is equilibria as the forward reaction is overall reaction is the exothermic minus 7.2 kg per mole. It means that the forward reaction is the exothermic, and the reverse or the backward reaction is endothermic. The reaction is reversible, and the reaction equilibrium is a closed system, so shows that how the rate of the forward reaction changes with the time. Initially, the rate of the reverse reaction is 0. Complete figure 2.1 to sketch how the rate of the reverse reaction changes with time. When we say equilibria, it means that this is the decrease in the concentration now. Maximum reactant at the start. So this line shows the decrease in concentration of reactants because reactants are maximum. So at the start, the products they have the zero concentration. So with the passage of time, the concentration of the reactants that will decrease, and the concentration of the product will increase. So we can say that when the concentration of the product, if it increases, the time will come when we'll get to equilibria. So if the concentration of the product is like that. When a time will come when these two lines join with each other, so we'll get a uh, no more change in concentration of reactant in the product, and this is the condition of a reversible reaction, that when this line increase the constant increase in concentration of product. Now, when the equilibrium has been established, it means that the rate of the forward reaction is exactly equals to the rate of reverse reaction, and no more change in concentration of reactants in the product, or the concentration of the product remains constant. Or we can also establish this equilibria like that. If this is the decrease in concentration of the reactants, and if this is the increase in the concentration of the product, and here when the two lines become straight, the equilibrium has been established. Either in this way or in this way, both are correct. Then state how the position of equilibrium changes, if at all, when the reaction takes place at 100 degrees Celsius. Explain your answer, and the pressure remains constant. So 100 degrees Celsius. If you look at your reaction, it is happening at 25 degrees Celsius, as the forward reaction is exothermic, because the overall reaction is exothermic. So that's why the forward reaction is exothermic. And you know that the exothermic reactions are favored at low temperatures. So if we look at the position of equilibria, when the reaction proceeds in the forward reaction, it is already releasing heat. So if we increase the temperature, from 25 to 100 degrees Celsius, what will happen? Equilibrium position, or the position of equilibrium, moves to left. So what will happen? At the position of equilibrium moves to left. Why it happens? As the forward reaction is exothermic, or we can say that the reverse reaction is endothermic. Now, for the next part, uh, this table shows the composition of an equilibrium mixture of nitrogen monoxide, dioxide, and then dinitrogen trioxide at 101 kPa. So this is the total pressure. This is the P total. Number of moles at equilibrium. So these are the moles of different gases at equilibrium. Calculate Kp. So the Kp expression is that the partial pressure of the products over partial pressure of the reactants. The product, this is the product, these are the two reactants. So partial pressure of N2O3 over partial pressure of NO times partial pressure of NO2. So the partial pressure of any substance or any gas can be calculated by multiplying the mole fraction with P total. And the mole fraction is that the moles of individual moles of that gas over total moles of that gas. And then if you multiply with the total pressure, you will get the partial pressure of this N2O3. Now, first of all, we have to calculate the total moles because we have to use the total moles. So the total moles are 0.605 plus 0.605 plus 0.390, which is equal to 1.60. Now, the mole fraction of both NO or NO2, because they have the same number of moles at equilibrium. So mole fraction of NO and NO2 separately. This is the individual moles of suppose NO, and this is the total moles of NO. So 0.3781254 for each. Then the mole fraction of N2O3, the moles of N2O3 are 0.390 divided by 1.60, because these are the total moles, so 0.24375. This is the mole fraction of N2O3. So if we put the values of in the terms of partial pressure, that Kp is The mole fraction of product is 0.24375 times 100. So this is the partial pressure. Then the mole fraction of both anode and NO2 is same, and 0.378125 times 100, then it's the partial pressure at the mole fraction. Partial pressure of both these gases same. So when we times it, we can do like this. And if we solve it, we will get 0.0170. Now, look at the unit of the total pressure. We have to follow that unit, which is the kPa. So kPa is the unit for N2O3, then kPa is the unit for both NO and NO2. So if we calculate the unit, we'll get kPa minus 1. So this is the answer along with the unit. And this is the way to find out the partial pressure. Identify one natural process and one man-made process that causes the formation of atmospheric NO and NO2. So natural process is the lightning, in which the atmospheric nitrogen reacts with the oxygen to form oxides of nitrogen. And the artificial process is internal combustion engine, in which the atmospheric nitrogen reacts at maximum temperature with the oxygen to form oxides of nitrogen. Now, NO2 is a brown gas that can be used to form nitric acid. NO2 is a free radical. Define the term free radical. The free radical is this species with one or more unpaired electrons. So the species with one or more or more unpaired electrons is radical or free radical. So NO2 has catalytic role in the oxidation of atmospheric sulfur dioxide. Write equations. So you have to write down the two equations to show the catalytic role of NO2. Catalytic role means catalyst. You have to show the two reaction. The first reaction in which the NO2 is used up. This is the reaction between NO2 and sulfur dioxide. So sulfur dioxide, we will get sulfur trioxide and NO. So the NO, if it combines with the more oxygen, we will get NO2. So this is the catalytic nature of NO2, that NO2 is consumed in the first process, and then we are getting at the end, because catalyst is it is not used up, it remains as it is at the end of the reaction. State one, environmental consequence of the oxidation of atmospheric sulfur dioxide. You know that the sulfur dioxide and nitrogen dioxide, they cause the acid rain. So they cause the acid rain. A student titrates nitric acid with the base to form solution containing aqueous magnesium nitrate. Identify the base that the student, okay, so the nitric acid and magnesium nitrate. So you have to write down the base of the magnesium, and the magnesium base is magnesium hydroxide. So this is magnesium hydroxide. The student evaporates the water to obtain magnesium nitrate solid. When this solid is heated, it decomposes. So the thermal decomposition of magnesium nitrate, this is very simple. This is magnesium nitrate. So if we heat magnesium nitrate, we'll get three products: magnesium oxide plus nitrogen dioxide plus oxygen. So if you want to balance, like you can balance like 2, 2, 4, or 1, 1, 2, half. 1, 1, 2, half. State how the thermal stability of the group 2 nitrate changes down the group. As we move from top to bottom, the thermal stability increases because cationic size increases. The reasons are not actually required in this question, but just for the knowledge of the students, the cationic size increases, and the polarization power of cation that decreases. So that's why it will be difficult for a cation to polarize the electronic cloud of anion towards itself and break a bond of Cn or NO. So thermal stability of the group 2 that increases from top to bottom. So in this session, I'm going to solve the two question. Uh, in the next session, I will be able to solve the rest of the paper. I hope you will get the maximum things from this paper. Thank you.